Yes, well, thank you very much to the organizer for this invitation to this special session, which has become a bit of a tradition at the MCA. I'm glad for it. Okay, so I will talk about p-adic equidistribution of CM points, and this is joint work with Sebastián Herrero and Juan Rivera-Letelier. So you can see their pictures here. Okay, let me start. So just let me start with the motivation for this work. The motivation is not p-adic, it's complex. So we will denote by y of c the moduli space of elliptic curves over C. So complex elliptic curves up to isomorphism over C, which is, as is very well known, this can be uniformized as a quotient of the upper half plane by SL2Z. And now we fix a discriminant that for us, this will be a negative integer, which is 0 or 1 mod 4. This integer determines a unique order of discriminant D inside the field Q squared root of D. And the main protagonist here will be the main characters will be the elements in the set HD, which will be the elliptic curves having an endomorphism ring isomorphic to OD. So this HD is a finite set, and by the classical CM theory, we know that the number of elements can be put into there is a correspondence with the Picard group of OD, or the class group of OD, if you prefer. And in this talk, so CM points are elements of this HD for some D. So yeah, isomorphism classes of elliptic curve with endomorphism ring being in an order inside a quadratic imaginary field. So there is a classic theorem proved by Duke in 1888, and then in full generality by Clozel and Ullmo, stating that the sets HD equidistribute on this complex modular curve as the discriminant goes to -infinity following the hyperbolic measure. So this theorem was proved by Duke, as I said, under the assumption that the discriminants are fundamental discriminants. And then Clozel and Ullmo extended his results to full generality. Now, equidistribution means something very concrete. This means that for any test function, call it f, from y of c to the real numbers, which is continuous and compactly supported, then when you average your function on the set HD, so you evaluate on every point and you divide by the number of elements in HD, then as D grows, as the absolute value of D grows, you will approach the integral of the function with respect to this measure, which is dx, dy, or y squared. This is the hyperbolic measure. And this factor 3 over pi is here just to normalize it, to make it a probability measure. Yeah. Okay, so that's classic result. So today I will talk about the p-adic case. So we fix a prime number p, and we will call CP a completion of QP bar. So this CP will be both complete and algebraically closed. So it will be like an analog of the complex numbers, but for p-adic numbers. And throughout this talk, we will fix an embedding of Q bar inside CP. There are many of them, so we fix one, once and for all. If we do that, then we can consider all these CM points. We can they are actually defined over Q bar. So actually, there is a very precise recipe of that tells you what's the field of definition of an elliptic curve with complex multiplication. But in particular, they are defined over Q bar. So we can see them as elements in the space Y of CP that I haven't defined, but Y of CP will be the moduli space of CP elliptic curves up to CP isomorphism. So it's the p-adic points of the modular curve. So, okay, so now the question is, the question we want to address is the following. So now take a sequence of discriminants, dn, such that the discriminants go to -infinity. So how are the sets HDN distributed inside this space YCP as n goes to infinity? That's the question that we want to answer. And what we will explain is that this is not like in the complex case, in the sense that the answer really depends on the given sequence. Yeah, so let me just go back to the complex case. In this complex case, there's no mention of sequences. I mean, any sequence of discriminants you take going to -infinity, you will find the same limiting behavior. But in the p-adic case, we'll see that it depends on the sequence. Well, I will explain how. Okay, so there will be essentially two types of results. So I will start with what we call the transient case. So what's transient? So by definition, the distribution of the sets HDN will be called transient if for every point in the complex p-adic modular curve, there exists a neighborhood U such that if you count the proportion of CM points falling inside U, then this proportion goes to 0 as n goes to infinity. So the distribution will be transient when CM points are not really are not accumulating anywhere. And so our first theorem that we prove with Sebastián and Juan is that it's a characterization on when this happens. So the distribution of the sets HDN is transient if and only if, and here is a condition on the, this condition is a condition on the sequence, which reads like the limit of the p super singular absolute value of dn is 0. Now I have to tell you what I mean by this, because this is I made up this for this talk. So let me explain that symbol. So any, as is very well known, any CM elliptic curve has potential good reduction. We call it E tilde here. It will be an elliptic curve over FP bar. So the p super singular absolute value will be, by definition, 0 if this E tilde is an ordinary elliptic curve, and will be the p-adic value of the absolute of the discriminant if E tilde is a super singular elliptic curve. So there are two ways, essentially, that when this can happen, the limit of the p super singular discriminant goes to 0. One possibility is that along your sequence, everyone has ordinary reduction. That's a possibility, because in that case, this symbol is 0 all the time. The other possibility is that all your elliptic curves, they have super singular reduction, but the exponent of p in the discriminant grows to infinity. So this is telling you that those are exactly the two situations where you should expect a transient behavior. Okay, so this is, well, this will be of no surprise for instance, it was very well known before we started that ordinary CM points of ordinary reduction form an isolated set p-adically. So if you're isolated, this has to be transient. Okay, but this is just a first. Okay, let me do a small comment. So the same theorem, but another way to phrase this transient behavior is as follows. Because in this transient behavior, you don't see a limiting measure. Yeah? but because it may seem that if there were some limiting measure, this measure will be the zero measure because there's no accumulation anywhere. But you can somehow put this in the framework of equidistribution using the language of Berkovich spaces. So if you identify y of Cp with Cp using the J invariant, then when you take the image by G of these Cm points, you get equidistribution towards a measure which is a Dirac measure, supported at a very special point, which is called Chi here, and it will be the Gauss point attached to the Berkovich line, the Gauss point attached to the unit disk. So you don't need to know Berkovich theory to understand and prove this theorem, but using the Berkovich theory, you can put it in the language of equidistribution. That is a limiting measure. Okay. So now I will explain the most interesting case, at least from my point of view, which is what we call the supersingular case. So now we will take a sequence of discriminants such that the reductions are always supersingular, and the p-adic valuation of the discriminant is fixed. We know already that if the p-adic valuation goes to infinity, then we have transient behavior. So we don't know what we want to know what happens in the opposite case. So we fixed the p-adic valuation. This translates, well, in particular, the completion of ODN, so the endomorphism ring of the elliptic curves, the completion at P will be an order in a quadratic extension of QP. Yeah, because in order to have supersingular reduction, your prime has to be either inert or ramified. So you will have exactly this. So with that in mind, now we will fix an order in a quadratic extension of QP, and we will concentrate on the set of elliptic curves such that the completion at P of the endomorphism ring is isomorphic to this order, O. And we look at the p-adic closure of that set. So there is here, this symbol here means that we are taking the closure with respect to the p-adic norm. This set will be called lambda O. Okay, so let me explain what we call the supersingular theorem in this case. That first of all, these sets lambda O are compact sets. Secondly, if I have two different orders, O and O prime, then this lambda, the corresponding lambda O's are disjoints. And the third point is the equidistribution statement is that, for simplicity, just to make it easier to explain, assume that P is 1 mod 4. This is a simplifying assumption. Then there exists a measure that we call mu O, with support equal to this lambda O, such that the sequence of sets HDN, which are subject to this condition, subject to the condition that ODN complete at P is fixed, it's isomorphic to O. Then that sequence equidistributes as dn goes to minus infinity with respect to this measure nu O. Yeah, so okay, this is again the same theorem. This did not change. I just want to do two small remarks. The first is that this assumption P equals 1 mod 4 is not at all necessary. It's just to avoid complications. If P is 2 or P is 3 mod 4, we have a more complicated statement but having the same structure. And the other observation is that I said at the beginning that we were fixing the p-adic valuation of the discriminant. And this is the same as fixing the p-adic completion of the order ODN. That's why this condition appears in this part of the statement. So fixing the completion at P of the order is the same as fixing the evaluation at P of the discriminant. Okay, so that's the situation in the p-adic setting. Now, I want to. I will try to say some words about the proof, but I would also like to make the point that these equidistribution statements, they can usually be they can be applied to Diophane time questions. So we have an application of that sort. So let me explain the application. So let me recall that what are singular moduli. Yeah. So the J invariant of a CM elliptic curve is by definition a singular modulus. And these singular moduli are algebraic integers. That is very well known. The theorem that we can prove using our result is the following. So you fix S a finite set of prime numbers and fix a singular modulus J0. It's fixed. Then the set that is written here, that is the set of all singular modulus J such that the difference J minus J0 is an S unit. Okay, so this set is finite. Okay, that's what our theorem is telling you. These differences of singular moduli are the subject of a very well-known article by Gross and Zage, where they work out a very nice formula for the factorization in primes of the absolute norm of a difference of singular moduli. And their formula is very, it can be very easily translated in an algorithm. And even in their paper, you can see lots of factorization of differences of singular moduli. It looks from these tables they write down that the number of primes has to grow with the discriminant. Yeah, they do a comment in that sense on their paper that these numbers are highly divisible, so prime numbers appear everywhere. And this result partially confirms this. It tells you that at least if you fix one of them and you compute the differences with all the others, then the set of prime numbers has to grow. Yeah, because to be an S unit means that the absolute norm is divisible exactly by the prime numbers inside S. So this is telling you that the number of primes has to well, the primes have to change, not necessarily grow, but to change. Okay, so this theorem is it's a generalization of an earlier result of Habegger. So Habegger showed he looked at this kind of sets, but when the set S is empty. Yeah. So when the set of prime numbers is empty, that so an empty unit is just an algebraic unit. So an algebraic integer such that the inverse is also an algebraic integer. So he proved that the set of singular moduli such that the difference is an algebraic unit is finite. And his method of proof uses the equidistribution of CM points on the complex modular curve. So this is for us, this result is really an application because we take his method and well, insert our p-adic result, and we obtain this generalization to S unit. Well, this result of Habegger and also our result is non-effective. We cannot say how many singular moduli are there. But there are some effective results on the algebraic unit case. So Biliu, Habegger, and Kühne in subsequent work, they show that if J0 is the singular moduli 0, which is a singular moduli, then this set is empty. So this is telling you that no singular moduli is an algebraic unit. And more generally, Jin-Kung Lee, he proved with a different method that no matter the J0 you put here, this set is empty if you really look for algebraic units. So okay, so these results are extremely effective, not only finite but empty. Yeah. But our result is non-effective, but more general because we allow any set of primes. Okay. So I will focus for the rest of the talk, so I don't want to be over time. So I will focus on how to apply our equidistribution theorem to this, to prove this statement about S units. Yeah, so this will be kind of publicity of how to use equidistribution statements for Diophantine questions. Okay, so this is essentially Habeger strategy, so I will explain that. So we will fix J0, so the J invariant of a CM-elliptic curve A0. And we will assume for contradiction that there are infinitely many singular moduli such that the difference is an S unit. So there will be a sequence of discriminants going to minus infinity such that, well, Jn will be the J invariant of En. Jn minus J0 is an S unit for all n. So a first ingredient is that these algebraic integers Jn minus J0, they are not small points. On the contrary, their height grows as the logarithm of the discriminant. Yeah, this is essentially, this comes back essentially to Colmet's formula, which has a long story, but the idea is that Colmet's formula gives you an expression for the Faltings height of a CM-elliptic curve in terms of an special value of an L function. And this special value can be bounded from below by this kind of quantity. And then this is not the Faltings height, this is just any veil height, but Faltings height and veil height are comparable, roughly comparable. So if you have this estimate for the Faltings height, you also have it for any veil height. Well, Colmet's formula is true for fundamental discriminants, so you need to do some more work to make this bound true for arbitrary discriminants, but it has been done by other people. Okay, so the idea will be to use the assumption that you have infinitely many S units to show that to show an upper bound on this height that contradicts this lower bound. Okay, so in order to do that, we will open the veil height as an expression involving all places of Q. So okay, so this formula here, it looks a bit weird, but it's really taking the definition of height and then doing some standard manipulations. So which manipulations? First of all, if you look at the formula for the height, you have what really matters are the Galois conjugates with absolute value bigger than 1. But here we are focusing on Galois conjugates with absolute values smaller than 1, or even smaller than R, where R is some quantity between 0 and 1. We can do that because of the product formula. The product formula tells you that the product over all valuations of an algebraic integer, which is non-zero, it's equals to 1. So by taking logarithms, you can pass from bigger than 1 to less than 1. That's a very standard manipulation. Then we are introducing a cutoff, so this R thing. So everything has absolute value less than 1, but we introduced cutoff there, R, that will optimize at some point. And we are we are using here that our assumption that everyone is an SC unit, because the only non-Archimedean places that will play a role are those Archimedean places related to the primes in S. For the other ones, the difference will always have absolute value equal to 1, so they will not appear because you take a logarithm, so they will not appear here. So okay, so you get this formula by standard manipulations and introducing some cutoff parameter R.
Excuse me, what was O again? How do you?
Oh, I'm sorry about that. Yeah, O. So I didn't explain what was O. So O is the Galois orbit of this algebraic integer Jn minus J0. So when you compute the height, you need to calculate the absolute value of all the conjugates of the algebraic number. So this is, which is the same as taking the Galois orbit. Oh no, wait. So okay, that's the O. Yeah, so let me just say one more thing, that here I am taking absolute values of Q, because it's either S or infinity. But I'm applying this to algebraic numbers that do not necessarily live in Q. So what I'm doing is taking some arbitrary extension and then use the Galois orbit to obtain the other extensions of every absolute value. So this is not the standard way to write down heights, because what we usually do is to take all the evaluation extending 1. But it's equivalent, and it has the advantage that it makes appear the Galois orbit, which is exactly what we need for equidistribution. Okay, so now I said that we wanted an upper bound. So what we will do is to take, you see, for every, this is a finite sum. So for every one of these places, we have an average of the function minus log over the Galois orbit of Jn minus J0. So what we want to do is to bound this kind of averages, sums of this form. Since there are a finite number of them, if we can bound every one of them in a convenient way, then we can add the bounds and get some conclusion. Okay, so how do we upper bound this? First, we show the following. This is, we show that the biatic value, the biatic absolute value between Gn and Jn and J0 cannot be too small. Yeah, so this is expressed in this way, that minus log of this is bounded from above by AV log of discriminant. This is saying that singular moduli cannot approximate another singular moduli too fast. There is some control on the rate of approximation given by the discriminant. This bound is part of Habeger's argument when the place is Archimedean. So it's written in his paper using, he uses these bounds by David and Hirata Kono on elliptic logarithms. When V is non-Archimedean, so we have also proved this bound. So this is a non-Archimedean analog of Habeger's bound. But the technique is a bit different. I won't delve into that, but it's an important step because we will use it now, as I will show. Okay, okay, this bound is a state for Gn minus J0, but it's also true for the Galois conjugates. So all this minus log of absolute value of alpha will be bounded in the end by some constant time logarithm of the absolute value of the discriminant. So this average here will be bounded by logarithm of the discriminant times the number of Galois conjugates that fall inside this disk of radius r. And that will be roughly the limiting measure of the disk with center J0 and radius r. Yeah, so something I should have said at the beginning is that since we are reasoning by contradiction, we can assume that the p-adic value of the discriminant is fixed, because we can take a subsequence where that happens. So this average of log of alpha is bounded by the measure times the upper bound, which is a logarithm of the discriminant. Okay, so now we just add these bounds. And in the end, we get that the height is bounded by some constant dependent on the number of places. Here we use that the S is finite. And then the sum of all the measures applied to these disks on this cutoff R. Now, in order to conclude, we need to prove that these measures are non-atomic. Okay, I won't go into details, but it's very similar to the fact that the hyperbolic measure in the complex setting that we can write down very explicitly, this is obviously a non-atomic measure. Well, you have to check it on the cusps, but it's also true. It turns out our limiting measures, they also have this property. They are non-atomic. So if R is small enough, you can do this quantity as small as you want. So by choosing R correctly, you can contradict the lower bound we had before. So let me remind you that the lower bound was constant times a logarithm. So upper bound is something that can be done really small times logarithm. So if you choose R small enough, you have a contradiction. Yeah, and I said nothing about this other term, but this other term is very easy to bound. It's also, this is very easy to bound. So, well, okay, so this is how you apply equidistribution to this kind of thing. So, well, I will stop here. So, thank you.
Questions for Ricardo? So you suppose, sorry.
Oh, sorry. About the proof of the main theorem, which, oh, maybe I was confused.
You mean the equidistribution theorem?
Yeah, that you, yeah.
I said nothing about the proof.
Okay, okay.
I can say a couple of words if you want.
Yeah, maybe.
Okay, so I was slightly prepared for that.
Oh,
It will take me like 3 minutes to give a rough idea. So the main idea is how we prove the supersingular theorem. So first of all, we have there is a finite number of supersingular elliptic curve over FP bar. So call them E1 up to EK. For every one of those, we will consider the set of p-adic elliptic curves reducing to, say, EJ. That will be the disk DEJ, and it's a disk. So the mental picture is that you have a finite number of points, the supersingular elliptic curves, and a disk above every one of those. So the strategy is to fix one of these supersingular elliptic curves, and then try to understand the asymptotic distribution of the CM points falling inside the corresponding disk. That's the idea. So now we will fix on one of those disks. Okay, and we can, just to explain the idea, we will do some simplifications. We can assume that our completion is a maximal order inside a quadratic extension of QP. that all discriminants are fundamental. So like in Duke's theorem, we can consider that. We'll also assume that P is not ramified. P is 1 mod 4, so the statement is less complicated. And we will also assume that there are no automorphisms of the supersingularity curve we are looking at. These assumptions are not serious. They can all be lifted, but since I want to explain the main idea, I will do that. Okay. So the thing is that the division quaternion algebra ramified exactly at P and infinity plays a role here, because as it is classically known, the completion at P of the endomorphism ring of E is isomorphic to the maximal order inside this quaternion algebra. Sorry, this is the quaternion algebra, the local one. This is the quaternion algebra over QP, which is a division algebra. Then you can use the deformation theory of the formal group attached to E to construct an action from OB star, the units, inside the E. So you want to realize this disk as a homogeneous space. That's what you would like to do. And we succeed in some way. Well, this deformation theory is Gross and Hopkins theory, very classical. So now inside the quaternion algebra, consider what we call a p-adic ball of radius L, where L is a p-adic integer. So this will be the set of elements in OB with trace 0 and norm equal to minus L. These are all units because L is it's a discriminant, so it's not divisible by P. Okay, so these are all units. And I will stop here. This is just to give the main point. The main point is the following, is that every point in this p-adic ball has a unique fixed point in the E. Such fixed point is an element of lambda O. And this will give you a uniformization. So the p-adic ball mod plus or minus 1 will be in a continuous bijection with lambda O by the map that takes G to its fixed point. So you cannot really uniformize the disk DE, but you can uniformize the closure of the locus of CM points where the completion of the endomorphism ring is fixed. So for every O, you have some kind of uniformization. And then you construct the measures and you run the argument in the quaternion algebra. And at the very end, you translate everything to the modular curve by pushing forward by this fixed point map. Okay, that's there are many more things to say, but this is the main construction.
So when P is 3 mod 4, you still get the measure, but not the equidistribution? Or why is the zero more complicated in that case?
Yeah, when P is 3 mod 4, this you cannot parameterize the whole of lambda O. You have to split lambda O into two sublocuses and parameterize separately every sublocus. And you can prove equidistribution, but in this sublocus.
I see.
And the reason you have that is that when P is street mod 4, there is a quadratic character which is there is a quadratic character that at P is -1, and for any prime different for P is 1. Yeah, you can prove that by genus theory, and that character splits things. So it's not too much complicated. I mean, only you need to split your locus in two sublocus.
Mm-hmm. There are no further questions. Let's thank Ricardo again.